Hello, everybody. Welcome to Chapter 4 Solids Handling for your certification review course. So, a real quick recap on what we've discussed so far. We started out with a general overview of the wastewater treatment process, and so far we've gone into detail with preliminary treatment. And if you recall, preliminary treatment was basically just getting rid of the big stuff in our waste stream: branches, rags, diapers, wipes, uh, any of that stuff that could damage downstream equipment like pumps or could create a problem with our downstream processes. We talked about that with preliminary treatment. The other thing we discussed with preliminary treatment was grit removal. And remember, grit is the sand or the pebbles or coffee grounds or inorganics that we want to get rid of before we start moving the wastewater on to primary treatment and then secondary treatment. Um, so we want to get rid of those or inorganics, again, the sand and what have you. And that's a grit removal system as well as a grit washing system. And the whole point of the grit washing system was to separate the organics in our wastewater stream from these solid inorganics, the sands, pebbles, what have you. That's going to save us time in the long run and cost in the long run. So after the preliminary treatment, we sent our wastewater, which is now, has very few inorganics in it and has a high level or concentration of organic material. And we sent that wastewater from the collection system. Well, let's talk about velocities. The collection system, we had a 2 foot per second velocity, and we did that to keep from the solids from settling out in our collection system. And in the preliminary treatment, we slowed that wastewater down to about 1 foot per second. And in the primary, we went down to about 0.03 to 0.05 feet per second because we really want to slow that wastewater down. And the suspended solids in that wastewater, we're sending that into a primary clarifier at a very slow volume where we allow those organic solids to settle down and form our sludge blanket. And as you may recall with the primary treatment, that sludge blanket in the primary clarifiers kept it about 5 to 8 feet thick or deep. And in the bottom of our circular clarifier, for example, we have a rake that is scraping and pushing that sludge down to the center where we pump it someplace. At least that's where we ended with the primary treatment chapter. Well, the someplace that we're sending it to now are places like digesters, gravity thickeners, and what have you. So that's the idea of solids handling. We are now trying to deal with these larger amount of solids that we're concentrating. Okay, so with solids handling, as you may well imagine, that can incur quite a bit of costs within our system. Okay, so think about it like this: the water, a portion of the wastewater stream, that's easy to move around, pumps, what have you. Yes, it incurs costs, but it's relatively easy to move that liquid or that high water content water or liquid solution around. With solids, we're dealing with more like a thickened sludge, like flowing mud, if you will, almost. And that solids handling, we can handle it with thickeners or a digester, and we are eventually going to want to dispose of that sludge. And that takes quite a bit of man and woman power, takes our operators working on this, and it can incur high plant expenses. So I think I've told you guys a few times, when we're managing a utility, we do worry about the small costs because all those small costs in treating wastewater, they add up because it's a 24/7, 365 days a year operation. That wastewater comes in every single hour, every single minute of every single day, month, and year. So even though we're talking about initial small costs, when you think about that volume coming in and the amount of solids we have to deal with, that adds up over time. And we want to be as frugal and as value oriented as possible. So that's why we're concerned with the solids handling, because it just basically has a high operational cost. And what we're trying to do with solid handling, one of the big objectives is we want to decrease the water volume in our sludge, increase the solids concentration, and we're doing this to save money. And think about it, we're concentrating the solids, so we're not hauling off wet sludge to a landfill. We're hauling off very concentrated solids. That's going to save us money over time, okay? A rule of thumb, one item you do want to remember. This is one of those things that'll come up in homework, in a final exam, as well as your certification exam. The rule of thumb in solids handling, when we double solids concentration, we are in effect cutting the required water moving volume in half. This will show up time and time and time again, okay? So I want to make sure you guys do get this down. Double the solids concentration decreases the water volume required to move things around by half, okay? So what does this mean? Well, when we start sending this sludge to these basins that are called digesters or sludge thickeners, gravity thickeners, we are using less water. And think about it like this. If you've ever looked at water characteristics, water has a high thermal capacity. What that means is if you heat it up, it's going to keep that heat for quite a while. When you cool it down, it's going to keep that reduced heat or colder temps for quite a while. It's going to take energy to increase the temperature or time and energy to decrease the temperature of water. Now, if you think about that, when we talked about microbial activity, we basically said that temperature swings, that'll affect microbial activity, right? So we can really increase microbial activity by heating up the water or warmer parts of the year. And then during the winter, colder parts of the year, microbial activity really starts to slow down. So the idea here is those swings can cause instability in our process. So by minimizing the water content in our sludge in these thickeners or digesters, we're creating a stable environment with which to operate. We're going to eliminate swings, high temperatures, as well as low temperatures, okay? By doing that, reducing that water input, we're going to reduce those temperature fluctuations, and we're going to reduce what's called return supernatant. What that means is the liquid part of that waste stream, we're not going to have to recycle it as much. It's not going to have to come through 2 or 3 times. It'll come through once, okay? So this leads us to what are called gravity thickeners. So we can move our wastewater stream around as much as we like. We can use pumps. We can do a lot of different things, but we're basically imparting energy. We're paying for energy. But think about this, in a primary clarifier, we were basically letting gravity, a zero cost energy source for us, handle the separation of those suspended solids down in our waste stream to form that sludge blanket. We're letting gravity do the work for us. Same kind of thing in a sludge or a gravity thickener when we're dealing with sludge, okay? We're basically dealing with a thickener that's another circular tank. It's a scaled clarifier, if you will. It's built the same way a primary clarifier is, with a few tweaks. The dimensions and flow rates, they're going to be designed and built for heavier sludges and lower flows. Recall that in the primary clarifier, we're bringing in pretty much the entire volume or flow of the waste stream, and it's more of a lighter material because our solids aren't as concentrated. But once we concentrate those solids into a sludge, we've still got a moisture content, but it's a lot heavier sludge, and they're lower flows that we're dealing with. So these thickeners, they're basically circular tanks that operate the same way as a primary clarifier, but they're dealing with thicker flows and or thicker contents in the sludge and lower flows because we're not bringing as much sludge into a gravity thickener as we are wastewater into a primary clarifier. Okay. Okay, the design rates that we're talking about, this is something you're going to see a few times uh, in level 3 and level 4. May see it in level 2, but definitely will in a level 3 and level 4. Your surface loading rate. So the volume coming in, the volume flow rate, divided by the cross-sectional area, that circular area, the top area of a thickener, that's your surface loading rate. The surface loading rate that you want to use in one of these sludge thickeners or gravity thickeners is 400 to 800 gallons per day per square foot. Okay, so you take the flow and you divide it by the cross-sectional area, the area of that circle, and that's where you come up with this. That's a number you should know by heart. Okay, and detention time in a thickener, that sludge is going to stay there 1 to 2 days under normal operations. Okay. So as you recall, detention time is simply the flow rate coming into a tank or a basin or what have you, divided by the volume of that basin. Okay. So you'll come up with a unit of time. So that sludge is going to stay in this digester or in this gravity thickener 1 to 2 days under normal operation. Okay. The efficiency, that's going to depend on a few things: your solids concentration, the temperature, both the ambient air temperature as well as that of your waste stream, and the settleability of the sludge. That's what's going to dictate how efficient these thickeners are. Okay. The sludge types, we're basically dealing with primary sludge at this point. Okay. At least what we've talked about so far. And primary sludge, you're looking at 4 to 6% solids volume in your sludge that's coming in. And primary sludge just means that's the sludge blanket formed in the primary clarifier coming into our thickener. That's all it means. So when you see primary sludge, that's sludge coming from the primary clarifier. Okay. Trickling filters, another item we talked about very briefly, but some places will use a trickling filter instead of a primary clarifier. And recall, with a trickling filter, we're basically pouring that wastewater over a rock, a filter composed of rock, and there's a little slime or biological coating that shows up on the surface of those rocks that are composed, or the filter media of our trickling filter. Well, the sludge coming off of that, rather than the 4 to 6% from a primary clarifier, you're looking at about 1 to 2% sludge coming off or formed from a trickling filter. Okay. Waste activated sludge, we talked a little bit about this in the intro. Waste activated sludge is sludge that's coming off your secondary clarifier. Okay. Primary sludge comes off of your primary clarifier. Waste activated sludge, that's going to come off your secondary clarifier. Okay. And the waste activated sludge, or WAS as you'll sometimes refer to, runs about 0.5% to 1% solids concentration. Okay. Let me go to the next slide here. Here we go. Uh, some of the things we're looking at with a gravity thickener or digester, we're trying to manage that sludge blanket. Okay. So we've got these vertical pickets or rake teeth, if you will. See if I can get you a picture here. So here's our rake, and here's what it's going to look like on the bottom. Not a great drawing, but our rake that's coming around the primary clarifier, it's got these vertical pickets, okay? And the idea of those vertical pickets is they look just like the rake, the teeth on your rake, if you will. Best way to think of it. So the idea here is it's gonna be on your rake, and it's gonna mix the blended sludges, and it's gonna release trapped gases. The reason we want to do this, to use those teeth to kind of blend the sludge as well as release trapped gases, we want to make sure we have a uniform sludge. Number one, it's going to make it easier to deal with. Number two, you remember what I told you? If there's any gases being formed in the sludge due to decomposition or microbial activity, what's going to happen is those microbes are going to expire CO2 or respire CO2. And that CO2 is going to uh, basically form little pockets of gas. And if you don't rake them up and break up that gas occasionally, if you have those small pockets of gas just getting big enough and then collapsing or expanding, uh, what's going to happen is if you have that and you don't release it on a regular basis, you're going to have sludge being put back into suspension. We don't want that because that will carry over to our secondary processes, and it'll just create a problem with dealing with our sludge blanket. Okay, so that's something we do want to avoid at all costs. Okay, the other thing we're looking at, let me get my little, there we go. We don't want that sludge blanket to go septic. Remember, septic basically means that we're losing our oxygen content. So we're going to form hydrogen sulfide gases, methane, as well as CO2. This can happen if we leave our sludge blanket in place in the primary clarifier too long, as well as in the gravity thickener or digester. If we leave that sludge in there too long, it's eventually going to go septic or anaerobic, and it's going to cause bad odors. And if you have anybody near a wastewater plant, whether it be near a highway, a business, a set of homes, a development, you want to avoid the odoriferous, is what it's called, the bad odors condition, because you're going to get complaints like there's no tomorrow. And once that starts, it's really never going to stop. Okay. You also want to eliminate those floating solids we talked about. If your sludge goes septic or anaerobic, it's going to eventually put those sludge particles, that flock that form the sludge, back into solution or suspension, and we don't want that. Also, it's going to lead to poor dewatering. It's going to cause us problems. As I mentioned earlier, if we have too low a solids concentration, it makes absolutely no sense to try and keep working with that. Okay, so uh, it'll cost a lot more, and it'll just be a mess if your sludge is too watery and doesn't have a high enough solids concentration. Uh, we want to maintain the target depth of your sludge blanket at about 5 to 8 feet. Okay, that's going to allow for all of these things to take care of themselves and for our blanket not to go septic or anaerobic. So here's the thing. If we ignore the management of our sludge blanket and we let it get deeper than the 5 to 8 feet, we're going to start increasing a required process detention time. What it means is we're going to create a mess for ourselves by and large. So if you let that blanket depth increase, you're going to increase the process detention time. And again, you're just eventually going to lose control of your process and create a mess for yourself. Okay. Here's something you do want to know, particularly if you're going for a level 3 or level 4 operator exam. There's this thing called a sludge volume ratio. There's also this thing called a sludge volume index. I will refer you to the Ragsdale chapter on mathematics for wastewater operation to look at how that's calculated. But the idea here is we're continually taking readings in our process, and we're going to use those readings, whether it be from a sludge judge or what have you. We're either going to calculate a sludge volume ratio or a sludge volume index. But that's what's going to allow us by keeping those two parameters, sludge volume index and sludge volume range, in a certain range or set of values. That's going to help us manage our sludge blanket. I encourage you, read ahead in this manual, take a look at the mathematics chapter, uh, play with some of the numbers. This is not a difficult number, neither is the sludge volume index to calculate, but I strongly encourage you to take a look at that, okay? We also have these side streams that we need to deal with, and they'll impact the efficiency of our process and what have you. The side streams, those are basically return plant flows. Let's say we had overflow on a certain process. We're not going to just send that on to secondary treatment or discharge it. So if we have these return flows from further up in the process, we have to manage that. Okay. And we are looking at effluent and suspended solids in milligrams per liter against the influent solids. Okay. So that's how basically we're comparing effluent, which is what's going out, our suspended solids are what's going out, versus the influent, what's coming into our plant. That's going to help us determine our efficiency of our removal process. And all you're doing with respect to that is you're saying, what are our suspended solids coming in, subtract what the suspended solids are going out, divided by the suspended solids coming in, and multiply that by 100. That's your efficiency. Okay. That's how you would calculate your efficiency for your removal. Again, take a look at the mathematics chapter. It's really not a difficult calculation, but it's one you do want to become familiar with, okay? You also have, again, side streams. And all a side stream is, it's a flow of wastewater that whether it overflowed or whether it got to a point that had to get recycled. That's the side stream, because what we're doing is we're taking that recycled flow from later down in the system and we're pumping it or draining it back to a point earlier than that process. That's side stream. So it's like streams coming in from the side to our current process. Okay. So solids handling processes return, if there's a side stream or return flow, it's going to have a high BOD coming in, biochemical oxygen demand coming in, and low or no oxygen coming to the plant head. So you get a double whammy. You get basically a bigger food source for your microbes, and you also get less oxygen coming in. So those are two things you have to deal with. I'm going to take a little bit of a side note here. This BOD, okay, that's biochemical oxygen demand, okay, this is really the food that the microbes are going to use in order to munch away and grow. So when you hear BOD, that's the organic load or the strength of the wastewater. That's also the food that the microbes are going to use. Okay, so start thinking in terms of food for the microbes. That's a BOD. All right. So in this process, you're also going to start running the superintendent's going to have you guys take some samples and run them to the lab. You're going to run BODs during this process, as well as suspended solids on thickener overflow. So if there's any water or wastewater that overflows the thickener, that's going to be tested every single shift, every 8 hours. You're going to run a BOD and run a suspended solids test. What does that mean for you? It means you got to know how to sample and then take it to the lab. The lab manager or lab chemist, whoever's working in there, that's who's going to run the test for you, okay? So that's what we're doing, but realize you got to do this every single shift. Whatever wastewater's overflowing from the digester or the gravity thickener, that's what you got to do. You also have to look at a comparison. So I told you that BOD is the food, okay? That's the food microbe ratio here. BOD is the F part of the food microbe ratio. We're going to find out a little bit later, there's this thing called mixed liquor suspended solids, MLSS. MLSS is basically the microbes of your process. So BOD is the food, the microbes are the mixed liquor suspended solids. We want to keep the food microbe ratios constant for different processes, whether it's a thickener or whether it's your secondary process, mainly for your secondary process. Now think about this. We talked about our secondary process as basically being an activated sludge process, or think of it as using microbes, the M here, to eat the food, the BOD, the F. The reason we want this food to microbe ratio in a reasonable range is because if there's not enough BOD, not enough food, our microbes are going to die off. And if there's too many microbes and not enough food, those microbes, they can start cannibalizing each other. They'll just start eating what's available, which could mean other microbes. Okay. So the food to microbe ratio, that's another calculation, particularly in the level 3 and level 4 exams. You're going to be expected to know how to calculate that food to microbe ratio. And then you're going to be expected to know what your proper food to microbe ratio should be for your secondary processes. Okay, that's a little ahead of where we're at now, but I wanted to bring this up. And once again, if you want to start looking at the mathematics chapter in the Ragsdale manual, I strongly encourage it. But this is one of those things you're going to have to know for a level 3, level 4. Okay, some risks to overload. So if we have a poor thickener performance, what that means is if the poor thickener performance would amount to not thickening the sludge enough, increasing the concentration of the solids, we would have more water than we typically want. And that water portion of what's coming out of the thickener or the digester, that's going to have a high BOD level, okay? And it's going to have a low oxygen level. So if our thickener isn't working well and we are sending more side stream, okay, that water back to the headworks or back to the beginning of our process, we're going to overload the secondary treatment. We're going to really mess this ratio up is what it amounts to, okay? A lot of things that we're balancing all at once. Okay. We talked about using dissolved air flotation as a method to separate grit from our organic load. Okay. Well, same thing happens here. We can use dissolved air flotation to thicken the waste activated sludge or the WAS. Okay. So this is ideal for activated sludge that's only got 1/10, 10% of the solids of primary sludge. So remember, primary sludge is coming off the primary clarifier. It's mainly using gravity, getting as much of the solids, suspended solids, out of solution or out of the waste stream as possible. For the WAS, we're pulling the WAS or the waste activated sludge off the secondary clarifier, okay? So that's when this can really help out, because the amount of sludge or solids in secondary treatment is much less than that of primary. So that dissolved air flotation really helps with the separation, okay? And what dissolved air flotation is doing, it's bubbling up air from the bottom of our tank or our clarifier, and those air bubbles are going to reduce the specific gravity of those particles of that sludge to below 1.0. It's going to float them up, okay, so that we can take them away. And the dissolved air flotation, it's going to help increase solids concentration to 2 to 4 by 2 to 4%, or to 2 to 4%. I'm sorry, not by, but it's going to increase solids concentrations to 2 to 4%, and that's going to be corresponding if we use our rule of doubling solids increases uh, water separates water volume by, or reduces water volume by half. Well, putting our solids concentration with dissolved air flotation in this process to 2 to 4%, we're going to reduce the water volume by 1/8 or 12.5%. Okay. Uh, what we basically are looking at here is we're using a DAF, or a dissolved air flotation tank. It's basically a rectangular tank. You're bubbling air through it, and then you bring that wastewater in, and the any of the organics that float to the top, we're going to use surface skimmers to get rid of it. We're also going to have a sludge collector at the bottom of the tank. Okay. The other thing we can do with this process is we can use polymers. We can add these chemicals so that it'll help trap the air bubbles and form large floatable sludge flocks. Okay, it's basically a coagulant similar to what you'll see in water treatment uh, in the coagulation phase, but a little different chemical, but that's what we're trying to do. We want to form settleable or floatable sludge flocks. Okay, that's what we're looking at doing. This is a schematic of a dissolved air flotation unit. Okay, here's our sludge skimmer. It's just a chain driven with little rakes or pickets. And what we're doing is we're taking these pickets, and as the scum floats to the top, it's going to rake the scum at the top down to this little capture area, and we're going to send it to the thickened sludge discharge area. Okay, and our basically our effluent's going to come in, or our effluent's right here, so our flow's coming in. Okay, and we're allowing it to settle out. We're bubbling up air. Okay, and that air is going to allow these floatables to go up and then scraped off, and they go to a thickened sludge clarifier. And if we have any sludge at the bottom, we've got this chain driven assembly with these little pickets, these little rake teeth, and they're just going to keep in a process uh, raking up that sludge. And that's what we're looking at. And if we have polymer that needs to come in, we'll feed it at the influence side. So our flow is coming from right to left in this case. We're going to dose it with polymer, which is going to help with the coagulation of the sludge. But rather than letting the sludge fall down, we're trying to get most of the stuff to go up to the surface and rake it off and send it to a thickener. But we can have some bottom sludge, and that's what we're looking at. Okay. And the effluent, the outflow is coming out here. Okay, it'll go up and go out to the secondary process. But if we have recycled flows, this is where it'll get to the headworks there, to the beginning of the process. So that's a dissolved air flotation unit. Kind of cool. Okay. So what we're looking at here, in order to work with the dissolved air flotation units and control the process of where we're at, we have to basically pump up air or oxygen at about 90 psi. So those bubbles I showed you where that's coming in, that's at about 90 psi. Okay, and we're going to have a drop in pressure. Okay, that's going to form those bubbles, uh, and that they're really small bubbles when they're coming out into our process. And the idea here is not to break up the sludge flock, but they're like micro bubbles, if you will, so that they're going to take that flock up to the top. Okay, we are also just as we do in a water treatment plant, we have jar tests. And what a jar test is basically we take a sample of our wastewater prior to this process. Okay. And then what we do is we dose like 10 jars, for example, with different concentrations of that polymer we're adding to act as a coagulant. And by doing that, we're going to find out what the optimal amount of our flocculant, or our chemical agent, that polymer, we're going to need to get to the best flocculation. So we'll do that in the jar test, and we'll scale it up to our dissolved air flotation unit. The idea here is we want to save as much money as possible in our process because we don't want to throw too much flock agent in there or coagulant in there, nor do we not want to throw enough. We want to make sure it's optimal, and that's what the jar test will help us do. Okay. Uh, there's this charging that takes place, and that's basically recirculating the air saturated watered polymer. You just stir it up for about 30 minutes before you add it to the sludge. Okay, you're basically conditioning it to work in an optimal manner before you inject it to your dissolved air flotation unit. Some control variables. You're going to want to remember some of these, okay? Uh, this is how we manage our dissolved air flotation unit. And again, pardon me, this is mainly level 3, level 4 stuff. What you'll be asked as a level 1 examinee is, what is this? What's a sludge rake? What's a shear pin? What's a torque indicator? All that stuff. And as a level 2, you're going to be expected to say, okay, that's what it is. This is what it does. As a level 3 and level 4, you're going to be expected to look at variables and look at different kinds of things and say, this is how I would operate my plant, okay? So some of the things you want to worry about or you want to be able to control with dissolved air flotation, the sludge, you can control the sludge and airflow rates. You can control, as an operator, the amount of sludge you're introducing into the dissolved air flotation unit. You can also control with your blower controls the airflow, the amount of air you're bubbling into this process, okay? The other thing you can control, the recirculation flow, what you're sending back to the headworks and to the beginning of the waste process, treatment process. You can control that by controlling the recirc flow. You can also control the back pressure, remember, of that air. Okay. You can also you can set the feed hopper for your polymer dosage, or if it's liquid, you can control the positive displacement pump discharge into your process, right? That's something you can control. You can also control the skimmer speed that we looked at. That skimmer that's skimming the top of that waste stream, that sludge that we're forming that we help float to the top. Okay, those are all things you can control. And this is what a unit process and schematic would look like for a dissolved air flotation unit. We have sludge that's coming in, okay, coming in basically from our primary clarifiers, our system, or our thickener, and we're feeding polymer into that influent, okay, with our positive displacement pump. We know what the optimum dose is, okay. Now we've got this air tank, okay, we've got this aeration pump, and we're basically putting that in with our recycled flow and mixing it with our sludge. So we can control this, remember? We can control this. We can also control the air here. Things we can look at controlling. So that's our sludge coming in, polymer hitting it, and our recycled flow that is now saturated with air coming in as well. And that's what's coming into our flotation unit. It's going to make its way through the unit, and we're skimming off the scum, remember? So water's traveling, or the wastewater is traveling from right to left. And as we move from right to left, that coagulant plus the air, that's going to allow the organics that which would normally settle out as sludge. We're using that air to make it rise to the top of the tank, and we're skimming it, and that's additional sludge, a thickened sludge that will discharge. Okay, our effluent, that'll just move out. Okay, that's basically the water portion of the wastewater column, if you will, and we can pull some of that off, and we can recirculate it with more air, and the whole process repeats itself. Please do take a look at the schematic in the Ragsdale manual. It's also in the NMED manual. So please do take a look at that. Walk yourself through it. Make sure you understand it. you will see this at least at a level 3 or 4. Okay, so moving along, you remember I told you I like the Ragsdale manual because if he puts something in a box, it's going to show up on your exam. Well, he put this in a box. Same thing we were just talking about. What can we control for our dissolved air flotation units? These are all things we can control. The sludge coming in, the airflow coming in, however we recirculate the flow, the back pressure, that skimmer speed, and the polymer dosage. Things you should remember. Okay. And at the end of this lecture, I'll talk to you a little bit about the NMED study guide, because the more I poke through that, the more I find that that is relevant and something you do want to look at. Okay. So we now have a thickened sludge, but that thickened sludge still has a relatively high water content that we just can't send it to the landfill. So we now want to decrease the water content even more. We're going to be able to do that with mechanical methods. We're going to dewater that thickened sludge. We can use a vacuum filter, a centrifuge, and a belt press. Most places you're going to find, most, not all, but you're looking at belt presses, particularly in New Mexico, okay? Mid-sized plants, what have you, okay? And you can find plants that'll have a couple of these. So let's take a look at each one of these. So again, we are now looking at the thickened sludge that we're removing from the digester or the gravity thickener or the dissolved air flotation unit. We've got our thickened sludge that's higher in solids concentration, but it's still got water in it. And we want to get rid of that water as much as possible to make it economic to send that sludge to a landfill. So a vacuum filter, and we'll see a couple of just bare schematics of this. A vacuum filter, it's a drum, it rotates through a conditioned sludge vat, and it sucks out water. That vacuum action will suck out water, and it'll increase your solids concentration in that sludge to 15 to 24%, which is pretty high. So it's very effective. Thing is, uh, there is an energy demand for it, a relatively high energy demand. By doing that, you're going to get a high amount of solids in what are called sludge cakes. That's basically solidified sludge, but it's going to suck up a lot of energy doing it. Your costs are going to go up. So that's why I tell you, you may not see this too much in this state because most folks here want to keep their process relatively cheap. You can use a centrifuge. And all a centrifuge is, it's going to take that thickened sludge, it's going to spin it around in a centrifuge, and the water is going to collect in the center and drain away, and it's going to be returned as a side stream. That's called centrate waste. And the solids are going to hit the sides of that centrifuge, and they're going to come down and they're going to be taken away. And the idea here is you're typically going to use like a batching method. You're going to do a full batch and then you'll stop, reload, do another full batch. That's what you're looking at. There are some places that'll use a continuous scrolling configuration. What that means is it doesn't take a batch and spit it and then move it around. It means it's spinning constantly, but that's a high amount of energy as well. Okay. And that's what we're looking at. So that's the vacuum filter we talked about, the centrifuge, the belt press. The reason this is used around here, it's a low tech method, and a belter filt press. Well, the word press implies you're just going to squeeze or press the water out of that thickened sludge, and that's what you're going to do. It's relatively simple. Here's the plus, it's relatively cost effective. And you can have a conditioning drum and then a couple of belts that are going to do this for you. And there's also another belt filter press that we'll talk about, but that's the one of them you look at. And all you're doing is you're just taking a couple of rollers on that belt press and you're squeezing as much water out of the sludge as you possibly can. It's actually fairly effective. Okay. But the water that's squeezed out of that sludge You can't just discharge it. You can't just drink it. You can't sell it. You've got to take that to the headworks. It's drainage is piped to the headworks, and then it comes back in again, typically high BOD and low oxygen on it. Okay. And this is what one of them looks like. This is a vacuum belt filter. So what's happening with this is you've got this big Mondo roller of sludge, and what's happening is you've got this drum. It's rolling through the outlet, the sludge outlet of your thickener. It's picking up the sludge, and then as it comes down, it's going to squeeze the sludge. And again, that centrate or filtrate's going to go back to the headworks, and the solids are going to get pumped out. Okay, that's all you're doing. Think of it as a big roller that the vacuum is helping with, but that's all it really is. And you've got this cake being formed, and the scraper takes it off, and that sludge cake goes out as for management as biosolids. Okay, and that's the side view of it. Okay, you basically have a sludge pool, and you've got this big drum rotating, and it's going to pick up some of the sludge. As it comes up, the sludge cake's going to dry, and you've got this belt here. And what's going to happen is it's going to be sent to a scraper and then to a belt press. Okay, so that's what's going on there. You can also have a mixer for your sludge pool here, as well as polymer feed, and then sludge feed comes in here. Okay, that's a vacuum belt filter process. There's also just a regular belt filter. Okay, let me go to the next slide here. And this is a scroll type. Same kind of thing, only you're using mainly a screw type process where you have these uh, belt presses kind of going through a screw. And again, you form a sludge cake and you dispose of it. So the sludge comes in here, you hit it with polymer, and it comes in here. If there's any centrate, okay, it's going to come down to the bottom here and get sent back to the headworks. But basically, what's happening is you've got that waste stream coming in, and think of it as like a torque. You're using a screw or a torque to get rid of the water from that sludge. Okay. This is a fairly low tech version of a belt filter press. This is the simplest method of the dewatering as possible, and this is why I think it's so popular, because it is low tech. And what you basically have is you've got your sludge from your thickener, your digester coming in, high amount of solids, and then you've got rollers here with a belt press, and they're all spinning. So what you're going to do is you're going to have the sludge come in, the roller's going to press it out, squeeze it out between these two belts. You got a lower belt and an upper belt. The sludge gets squeezed in between the two belts, and all the way through there's these little rollers or bollards, horizontally mounted bollards, if you will, and they're going to squeeze the water out of that sludge. And as it comes out towards the back end, the bottom, it's going to do one last squeeze, and it's basically going to go off to the landfill. It's a fairly dewatered, high solids concentration sludge here. Okay. Uh, and it even gives you zones here. I don't think you really need to remember these, but it's always good to look at it. This is your draining zone where you've picked up the sludge, you're letting the sludge drain. You're not squeezing it too hard, but you are squeezing it. That's the draining zone. Most of your water solutions or centrate's going to come out here. The press zone is you now have those two belts, upper and lower belt, squeezing as much as possible to get that centrate away from the solids. And then you have the shear zone here, which is basically just pressing the heck out of your sludge cake and then discharging it at the tail end of the belt press. Okay. So that's it for this lecture. I put up a comment or discussion. If you have questions about this chapter, please ask. Okay. If you have any comments or feedback, you're going to get another weekly quiz, a feedback quiz, if you will. Um, just tell me what you're learning, things you want to see changed, what have you, and I'll adjust. But please do fill that out. Even if it's a one word or a few words, I'm good, whatever, but please fill it out. I also put together a 10-question quiz in the module. You have unlimited attempts. Now, a little change is coming up. Nathan had a really good question the other day, and I looked at the study guide from NMED, and I said, you know what, guys? We're not going to leave anything to chance. We're going to look at both the Ragsdale manual and the NMED study guide. I'm still going to tell you, I think the majority of your questions are going to come from the Ragsdale manual. I truly believe that. However, there are some that it looks like will come from the NMED study guide, and I want you to be prepared. So we're going to start incorporating material at the lecture from both sources, as well as give you quizzes from both sources. My intention here is not to be really harsh on or hard on you guys. My intention, though, is to get you ready and help you study for your certification exams, because I think you'd rather have your certification than you would A or B in the class. I mean, I just want to make sure I impart good study processes and material information to you, okay? So I'm going to start incorporating the NMED study guide material into the next lecture. What does it mean? The next lecture is digestion, which is solids concentration. So we can have a little bit of the stuff that we talked about now repeated, not all of it, but a bit of it. Okay. But again, I want to help you study. So read through both guides, get the concepts and major points from Ragsdale, because I think by and large, he's going to explain stuff so well relative to everything else. But the enemy study guide, it does look like you'll get some trivial pursuit there. Okay. So I want you guys to be ready. Um, I also did not include any videos in this PowerPoint, but I posted, I want to say, about 9 or 10 videos for you this chapter. Please do look at them. Please do watch them. Please. Um, if you wouldn't mind, if you could please shoot me an email when you see this video, just so I know that everybody's keeping up, I'd appreciate it. Please keep up with your weekly or each module's quiz or homework, if you want to call it that. Keep up with those. Please don't wait till the last minute. Don't wait till the end of the semester. Please keep up with those. Please give me the feedback quizzes. Okay. So this is your Tuesday lecture. I am probably going to throw 2 more lectures out at you this week. Uh, and I think we're making some really good progress. But please, if you have any questions or any concerns, please do tell me, okay? That's all there is for this module, but I look forward to hearing from you guys, and I hope this is helpful material for you. Thank you. Good night.